Great. So one thing that I want to just highlight here, what we've done now in terms of the computations here above, was that we had to compute lots and lots of integrals. Okay, and so we could compute them using a hyperintegrate because we had symbolic integrals. But when it comes to doing these things numerically, what if these expressions that we had were expressions that we could evaluate essentially only numerically? We didn't have them in a symbolic form. Because usually when it comes to finite element methods or any kind of numerical methods on a computer, using symbolic expressions is essentially quite expensive. So that's the compute and the compilers are not very good when it comes to symbolic expressions. And almost always these things are expressed numerically. It's almost like you say you have a function, you could evaluate it somewhere at a specific number and out pops the answer. And doing these integrals then in that world where we don't have these expressions explicitly, but we have them in a sort of an evaluatable form, makes it can become quite expensive if we don't do it properly. You can imagine we are doing here for a small little system, there's already 9 integrals that we have to compute. This is for a very small 3 variables problem. In a finite element problem, this often is, let's say, 500 million variables that we want to solve, of 200 million variables that we would like to solve. Then computing these integrals inefficiently is a difference between waiting, let's say, a couple of hours for an answer versus a couple of months. So this is really why it's so important that we do it properly. And this is also why the finite element community took such a long, spent such a long time investigating what works well for numerical integration, because the quicker you can make this, the quicker you make the solution to this process. Okay, so although this is an integral approximation approach, this will translate, as you saw with yesterday's weak form problem, this translates also to the finite element method, where we had the weighted residual problem and we approximated there. So this is essentially the bottleneck in the compute, is to construct these matrices and to construct these right-hand size. And so we want to try and do it efficiently. This brings us essentially then to sort of the page 214 to 217 of the prescribed textbook. So if you have a textbook that is not part of this version, maybe the 4th edition or something, just go to the back of the index and search for Gauss Quadrature, for instance. And what the Gauss Quadrature is essentially a way for us to evaluate the integral. So look at this. This is quite funky. It's to evaluate the integral between our two bounds that are between -1 and 1. So, but if I want to integrate f of x, I can do this integral by just evaluating the function at a couple of spots and multiplying with specific weights. So this is what this allows me to do, is to say I can go and repeat this integral. Yeah, instead of doing this integral by hand or analytically, I could actually do this integral by just evaluating the function at a couple of spots. And the nice thing is if this f of x is a polynomial, yeah, a polynomial function, so just something like x squared or x to the power of 3, then when I use enough of these points, my integral is actually exact. This is what Gauss figured out way back a couple of 100 years ago. So this is quite impressive result. So what we're going to be doing is we don't have to stress if this f of x is not explicit a symbolic expression, but it's just a function we can evaluate. And we plug a value in for psi I, and we out pops an answer for the f of psi I. We multiply it by some weight, and we keep on summing, and then we've integrated that f of x from -1 to 1. This definite integral has then been computed. This is what the Gauss Quadrature is about. Okay, so for one, the Gauss Quadrature is defined between -1 and 1. This is sort of the standard form for it. So this is also, later on you see when we start doing the finite element method, we're going to be choosing sort of domains for our functions when we start mapping functions from one domain to another domain. And the domain that we map to, we'll choose on purpose between -1 and 1, because it will make our integration easier. This is essentially the choices that we'll see later on reflecting in the course. Okay. So the question is, how many points do we need to use to exactly integrate a polynomial? So well, the fact of the matter is, if we have n points, we can integrate an 2n minus 1 polynomial. So a polynomial with degree 2n minus 1. Exactly. So what it means is, if I have 3 points, then I can evaluate 2 times 3 is 6 minus 1, a 5th order polynomial. So that is x to the 5. and lower terms, x to the 4 plus x to the 3, whatever. But the highest order polynomial, the highest term in that polynomial degree can then be 5, and then this integral will be exact. I only have to evaluate this function at 5 spots, and I have these 5 magic weights that I multiply them with, and sum them, and I've computed the integral. This is the beauty of the Gauss quadrature. Okay, so Gauss quadrature and Gauss integration allows us to really efficiently and effectively compute integrals in a very quick way. So it's one of the workhorses of the finite element method, is that we start moving away from this symbolic environment more and more towards a numerical environment where we want to compute these integrals efficiently, and then essentially Gauss quadrature is the answer. And this is quite useful, especially if we choose sort of quadratic, or let's go, polynomials for our shape functions and stuff like that, polynomials for our displacement fields, to have this kind of polynomial forms. Then the Gauss quadrature is very efficient. Okay. So here's just an example of how, where that psi I, so this psi is always between -1 and 1. It's in that domain where I need to evaluate if I want to use n equals 1 Gauss point. So let's just check again. If I have n equals to 1, what is the order of the polynomial I can integrate? Well, any linear polynomial, any linear thing I can integrate exactly. Can you see that? So that's essentially what this allows me to do. So any linear line, I can integrate exactly. So any linear polynomial I can integrate exactly using only 1 Gauss point. So what I have to do is I evaluate that line, what I have, for instance, at 0, and I multiply by the weight of 2. And that answer is then the same as the integral from -1 to 1. Now, if I have 2 Gauss points, I can integrate a third order polynomial exactly. Anything up to a third order polynomial I can integrate exactly. So that is a cubic. So anything up to a cubic allows me to do that exact. Then I need to evaluate it essentially at these 2 points, plus -1 over square root of 3, and the weight is 1. If you have 3 Gauss points, 3 Gauss points we know now as a 5th order polynomial. These are the places, the plus minus this value and a 0. This plus minus values have a weight of 5 over 9. This value has a weight of 8 over 9. And then a 4th order polynomial. 4th order polynomial, I can integrate anything up in until a 7th order term, anything up to 7 orders. I can integrate exactly, and these are the 4 spots and the weights associated with those 4 spots. If I have a 5th order polynomial, that allows me to integrate everything up in until 9 orders exactly, and these are essentially then the 5 locations, 2, 4, 5, and the weights associated with those locations. And this list goes on and on and on. But this is what Gauss quadrature allows us to do, is to really efficiently compute these integrals. Okay, so let's put this to the test, and then we can ask a couple of questions. So the first thing is I'm going to say, let's integrate this this polynomial here, 6 psi to the power 3 plus 5 psi squared plus 4 psi plus 3 between -1 and 1. So we can start off by saying, let's integrate this thing analytically. So what I'm doing is I'm just feeding in this polynomial, and I'm integrating it from -1 to 1. And there's the answer. Okay, now we're going to say, let's try this with Gauss quadrature. I know that I've got here up to until a 3rd order polynomial. Okay, so if I've got a 3rd order polynomial, I can say, well, what I would like to be able to do is to choose the right number of Gauss points. And if I choose 2 Gauss points, that allows me to say I can go up until the 3rd order or cubic term would be exact. So if I use 2 Gauss points, this integral must be exact. So let's check if it's true. So first off, there's the function. It's the same function as what I've defined here. The only difference now is this is now a numerical function, so I call it psi. And then I can say, to integrate this, we essentially have to evaluate it at minus. So the location is -1 over square root of 3, the weight is 1, and then +1 over square root of 3, the weight is 1. So that's what I've got here. -1 over square root of 3, the weight of 1, and +1 over square root of 3, and the weight of 1. If I take these 2 values and add them together, I can show you that the integral is now exact. Can you see that? Numerically exact. So this 6 is a numerical precision issue, but essentially up and until machine precision, this is exact. Okay, so that's the first point here. So just to confirm, you can see for yourself, you can do it this way, or now we're just doing 2 function evaluations, we can compute the same integral because this is a polynomial. Remember, Gauss quadrature only works for polynomials. As soon as I have something that's not a polynomial, I might end up having to have infinite number of these terms that I have to add for it to work. Okay, what if the domains are not between -1 and 1? So what if I have to integrate something between 5 and 10? So for instance, I want to integrate f of x, 7x to the power 3 plus x squared plus 4x plus 1 between 5 and 10. Okay, how can I do this? Okay, Well, first off, I can start off by saying this domain, can I maybe not transform this domain from 5 to 10 that's integrated over x to a domain from -1 to 1 that's over psi? Surely I'll be able to map that to say if x equals to 5, I want it to be such that I'm at psi equals to -1. If I'm at x equals to 10, I want to be at a place where I'm at psi equals to 1. So essentially this is what I can set up and say I want to see what that map thing should look like. So if x is 5, I want psi -1, and if x is 10, I want psi equals to 1. Okay, so this is the first point that I would like to be able to relate. The other thing I need to be able to do is to say that this dx is now dx in this x domain. I need to be able to relate it to this d psi in this psi domain. Okay, so the best way and the easiest way to do this is to say, okay, let's build this mapping. So I know essentially this mapping that I want to, I could maybe say, let's build a linear mapping for x to psi. Okay, so that like I mentioned, at psi -1, I want to be at x equals to 5. At psi equals to 1, I want to be x equals to 10, but I want to have this to scale linearly in between as well. This is what I'm setting up here. So the question is just what should a and b as the coefficients be? There's various ways you can go about solving it. The easy one to say is, well, a is the slope. Okay, if a is the slope, then I can say, okay, so what is essentially the slope? It's 10 minus 5, yeah, divided by what is the change here? It's 2. 1 and -1 is a difference of 2. So 5 divided by 2 could give me sort of the difference for the slope there. That's one thing I could do there, for instance. And the question is, what is sort of the intercept part here? Remember, I'm going from -1 to 1 here. So this intercept part, I can say it should maybe be the average between these two. So if I'm at the middle of this domain, and that is essentially 7.5, yeah. So, or just 10 plus 5 divided by 2. If I'm in the middle of this domain, then essentially going from minus psi, I'll be subtracting. Going from plus psi, plus 1, I'll be adding. So that allows me then to have that mapping. Because remember, this is what I'm doing. I'm adding and making psi -1 and +1. So this is a logical way of deriving it. If you're not comfortable doing it that way, and you prefer to do it sort of, so this is a reasoning out kind of approach. If you want to do it sort of more formally, you can just easily say, okay, at psi equals to -1, x is 5. First equation, psi equals to 1, x is 10. Second equation, 2 by 2 system linear equations, solve for a and b, and we can then solve. And when you solve it, you'll see you'll recover sort of the slope and intercept that we reasoned out. Okay, either way you feel, you do follow the approach that you're comfortable with. Okay, and then if you want to, we need to be able to relate dx to d psi. How do we do that? Oh, it's nice, because now we have an explicit expression of x, so we can just differentiate it. So let's differentiate x with respect to psi, so that's dx d psi is equal to a. Yeah, and then I can just say, oh, so dx is equal to 5 over 2 d psi by multiplying this d psi across, and there I have my expression for how dx relates to d psi. Now this allows me to say that if I want to integrate f of x from 5 to 10, I can integrate this new x as a function of psi over the domain -1 and 1. And this is what it allows me to do. So I can go and say, let's do this analytical first, just to make sure everything is hunky-dory. So here's what? This is the analytical integral of that, evaluate f, and here's the Gauss Quadrature. So yes, this is what I want to demonstrate. So this is first just doing the analytical integral. Okay, so that's that. This is the answer that we want to try and recover. And then if I go and I say, let's evaluate my numerical function, yeah, where I'm setting up my, now, let me just double check quickly. Where did I define f numeric now? Ah, sorry, yeah. So here's my numerical function, f numeric. It's just this numerical function of that expression that I would like to integrate. Same one here, that expression there. And essentially what I'm going to do is that I'm going to, what I'm going to do is I'm going to take a psi and then map the psi to an x. So this is what this do. If I feed in a psi, the psi will get mapped to the right x, and then I'll evaluate this expression at the correct x, because this expression is in the x world, and this is my mapping from psi to x, because I want to integrate, remember, from -1 to 1. Okay, so let's go and see what happens if we go this route. So essentially, if I want to do this integral from -1 to 1, then I can say, take the, again, before I do the integral, it's a third order polynomial. I forgot to just mention that. So that's third order. So 2 Gauss points is sufficient. So 2 Gauss points, we know the weight is 1 and 1. That's important. The F numeric, I'm evaluating it now at psi minus a third, minus 1 over square root of 3. And the other one I'm evaluating at 1 over square root of 3. This is what x1 and x2 relates to. This is the x value at psi minus 1 over square root of 3. And this is the x value at psi 1 over square root of 3. And so this is what the numerical values, I'm at least evaluating at the right axis, because this, again, this expression is in the x world. And this integral is not complete because I have not related now the dx to the psi kind of scaling factor. So if I want to do the integral in the dx world, I have to multiply by 5 over 2 to transform this the psi integral to a dx integral. So that's that 5 over 2 that I multiply by. Now I'm sure I've scaled it properly, and if I do this, I can see, boom, Bob's your uncle. I've got an exact integral there. And now we are comfortable of doing integrals using Gauss quadratures in different domains. You need to be able to scale that comfortably. And this is our first steps towards opening up sort of the general form of the finite element method. Later on, you'll see this kind of mapping that we are doing here from this x domain to this psi domain is what we actually call sort of, well, it's related to the isoparametric formulation. Okay. Something that will make sense a bit later, because it's more to it than just this, but essentially this is part of the first steps of saying any domain of x that we might have from 5 to 10 or 1 to 2 or 3 to 4, we can always map to sort of this domain, and in this domain we can do the Gauss quadrature integration. So hopefully this all allows you to see why we're making certain choices, and hopefully this will also motivate them nicely for you when we start making these choices later on, that you understand that some of the choices will be motivated by the fact that we want to use Gauss quadrature to essentially do the integration.